part of chapter 10. And here we are talking about the relation between linear and rotational quantities. For example, like you are giving me the rotational quantities, I want to find the linear, or you are giving me the linear, you want to get the rotational. And just here, we can say that all the velocity is going to be the tangent to the circle here, which means the average is going to be delta S over delta T. And if I will say delta theta is delta S over R, then I will say delta S equals R times delta theta. Then I can plug in this here, and then I can also say that omega is delta theta over delta T, and from that I can say the tangential velocity here, it is R times omega. This is a new equation. Then if you know like how many radians the object is making in 1 second, you will be able to calculate the tangential velocity as R times omega. Now, a very important, I will say, result here that you're going to notice is that if omega, of course, omega is going to be the same, then based on where the object is located, its linear velocity is going to change. Because if it is closer to the axis of rotation or to the center, then R is going to be short, and then we will have that object moving with less speed if maybe the object is at the rim. Okay, then I will say this is one of the relations, and we can apply this on this example here. Bonnie sits on the outer rim of a merry-go-round, and Clyde sits midway between the center and the rim. The merry-go-round makes one complete revolutions every 2 seconds, and we can conclude here that Clyde's angular velocity is of course the same as Pony's, because we are talking about how many revolutions is made per second. If I wish to calculate or find out the tangential, or like sometimes we call it the linear velocity is V equals omega R. Then this one is constant, then R, when R is short, we are going to have this less speed. Then who has the larger linear tangential velocity? Of course, Bonnie, because Bonnie is, look here, is at the rim, whereas the Clyde is in between. And of course, if it is midway, it's going to be half. Now, also, we can conclude another relation between the accelerations, and we can say AT equals R times alpha. And again, A is the tangential speed, tangential acceleration, sorry. We can, of course, also, and I think like I need to remind you here with what we did before. We said if my object is moving in a circle, and let's say the velocity now, it is not only changing direction, it is changing magnitude, then I'm gonna have two components for the acceleration. This one we call it centripetal acceleration or radial acceleration, and there is another acceleration, it might be in this direction or the opposite direction. And then here, when I have these two accelerations, this one, I don't know why sometimes it's changing into an eraser. Okay, and then here, I said this is the AT. And then I will say here, like what the object is gonna feel is the resultant of these two accelerations, and that is really A. Now, A tangential, it is needed to change magnitude, and AC or A radial, it is to change direction. I can use Pythagorean to calculate A as square root of AT squared plus AC squared. And of course, I can calculate the angle also as well. Then here, simply we're saying A as a vector equals AT as a vector plus AR as a vector, or AC. Then we add them as vectors. And since they have 90 degrees between them, I can use the Pythagorean to calculate the magnitude. And of course, like I can also calculate theta, the angle that is making with any of the axes, or phi here in the diagram. Tan inverse of, in this one here, is going to be AR over AT. Okay, then this is how we calculate the magnitude and direction of the total acceleration. Now, this is Jeff of the jungle swings on a vine that is 7.2 meters long. Suppose that at some point in this swing, Jeff has an angular speed of 0.85 radians per second, and at an angular acceleration of 0.620 radians per second square. Find the magnitude of the centripetal tangential and total accelerations. Then we want to find the tangential, centripetal, and total, and the angle that total acceleration makes with respect to the tangential direction of the motion. Omega is 0.850 radians per second. Alpha is 0.620 meters, radians per second square, sorry. And AC equals AR. We know that it is V squared over R, which is omega squared R squared over R, which means is going to be omega squared R. And then this is going to be 0.850 radians per second squared times 7.20. And from that, we can get the acceleration as 5. And this is the centripetal or the radial as 5.2 meters per second square. I can calculate the magnitude as square root of AC squared plus AT squared. And AT equals alpha times R, which is 0.620 times 7.2, which is 4.46 meters per second. I have the two values, then I will use Pythagorean to calculate A, and theta is tan inverse of A R over AT, and it is 49.4. Because we are adding them as vectors. Also related to the rotational motion is these parameters that I'm going to look at here. The first one is the period, which is the time needed for one revolution, and T equals 2 pi over omega. And the frequency, it is 1 over T, and it is omega over 2 pi, which means omega is 2 pi times the frequency. These some of the definitions that we will need also when we go to oscillations. Now, ironic motion here, we are going to talk about a motion that is going to be a combination of a translation plus rotation. Okay, and in this diagram here, I have a wheel that is rolling without slipping. We can see that this point here, which is in touch with the ground, is instantaneously at rest. then like when it is touching is going to be at rest, and the center moves with the velocity v. Now also I can say that the same wheel is seen from a reference frame where C is at rest, okay, like the center. Now point P is moving with a velocity that is negative v, and the linear speed of the wheel is related to its angular by v tangential equals r times omega. Now if we have any object that is round, like a sphere, a cylinder, anything, rolls without slipping, there is a fixed rotation relationship between the translational and rotational speeds. And that one, it is the case. V equals R omega equals Vt. This is only valid when I have an object that is rolling without slipping. Then I can, if I have the V in an equation, I can remove it and put R omega, because in this case, the velocity is going to be like when the object is going to move that distance, one cycle, is going to make a distance that is 2 pi times R, and the time for it to complete this is capital T, which is the period. We can also consider rolling as a combination or as adding pure rotation and pure translation. Okay, in A here we have pure rotation, and in B we have a pure translation, and then we added them. You are going to find that this here point is going to be at 0 because it is R omega minus R omega. This one here is going to move with R omega plus R omega, R omega plus 0, then it's going to be R omega. And this one here is going to move with R omega plus R omega, which is going to be 2R omega, which means as if instantaneously the object always is rotating about this axis here. And of course, as you go away from the axis, you will have more speed depending on your radius. Let's try solving this one here. The tires of a car make 65 revolutions as the car reduces its speed uniformly from 95 kilometers per hour to 45. The tires have a diameter of 0.8 meters. Okay, and we are asking now here what was the angular acceleration of the tires, and if the car continues to decelerate at this rate, how much more time is required for it to stop. Here I will say theta is 65 revolutions. V, this is the linear velocity of the car, and the initial, it is 95 kilometers per hour. V, it is 45 kilometers per hour, and the diameter is 0.8, and I want to find the radius as 0.4. I have here converted my velocities first into meters per second, and then I have calculated my angular speed for the initial one, which is 66 radians per second. I also calculated my final here linear velocity 12.5, and I have calculated omega by dividing this by the radius, and which is 31.25 radians per second. Now I have enough information to calculate alpha, and that is by just having this table here, which I have the initial angular velocity, the final, and I have theta, and I have to calculate alpha. Using that equation, I will be able to calculate alpha as negative 4.1 radians per second squared. In chapter B, we are asking if the car is still gonna have the same acceleration, how much more time is required for it to stop. Remember, we use sometimes that we might use the term deceleration, but the term acceleration is not wrong. Okay, and I will say here we can have this information and we will be able to calculate the time for it to stop. The initial velocity is 31.25 and the final is 0 and alpha is negative. Don't forget negative 4.1 and t is to be calculated. And t here equals 7.6. Now I can say that I want to talk about conservation of energy and whenever I have rotation, and then I will say the total kinetic energy of an object that is rolling. Remember, it has a translational or linear and it has rotational. Then this is gonna be for linear 1/2 mv squared, and it's gonna have the rotational, which is 1/2 I omega squared. Then I can here say, what is this I here? This I here, we call it rotational inertia, or we call it moment of inertia. And it is giving us how much the object is resisting the changes in its rotation motion. Now that I, it depends on many things here related to the object, like the shape of the object, and also the axis of rotation. Of course, I will say it depends on the radius and mass, but we will talk about this later, okay? But for now, I want you to know that the shape is going to be affecting. Now, I can here say that my I is, if it is given as a number, if it is given as an equation, you need to go to the chapter 10 table, and you will find all the equations for different shapes. Okay, now you're going to find that I is in general a constant times mr squared. M is the mass in kilograms, and R is the radius. Here, for example, I'm gonna say that for the sphere rotating about its center of mass, I for the sphere, it is 2/5 mr squared. For a solid cylinder, it is I, again, rotating with, the same, like about its center of mass is going to be 1/2. For a hoop, it's going to be different. Then it depends on which shape I'm looking for. And I will say here, we can use conservation of energy, both rotational and translational, should be taken into account. If I have an object that is going to be, I will say rolling down an incline. Okay, you can compare here. Like if I have a hoop, if I have an empty can, if I have a solid cylinder, or if I have a sphere, or I have a box that is sliding, what is really the difference between all of them Okay, it depends on how much rotational inertia we're gonna have in these, because initially all of them they're gonna have, if they're gonna roll down an incline like this, or if they're gonna slide, they're gonna have that amount of gravitational potential energy. If these two objects here, I have a hoop and I have a sphere, this is not a sphere, it's gonna be a cylinder, I know from the equation. If they have the same mass and radius, okay, and they are released simultaneously, the disk will reach the bottom first. More of its gravitational potential energy becomes translational and less rotational. Okay, and I will say we can apply conservation of momentum. 1/2 mv1 squared plus mgy1 equals 1/2 mv2 squared plus 1/2 I omega squared plus mgy2. Now, one of the things that I want you to know, even if they are not the same mass and the same radius, I will say we're gonna see that it's not gonna affect, because the mass and the radius, they are going to cancel. Here, calculate the speeds of the disk or the hoop at the bottom of the inclined plane if the height of the incline is 0.82. Using energy conservations, okay, I will solve for this. Here I did solve for the hoop, number 1. I will say at here, okay, let's see, this one is I, and this one is final. Then at I is going to have only gravitational potential energy. When it will reach my final position, this is my UG equals 0, then it's going to have only kinetic, rotational, and kinetic linear, 1/2 mv squared plus 1/2 I omega squared. And I can substitute my omega squared to be v squared over r squared, and I can cancel the mass because it appears on all the terms. Then finally I can conclude that my v squared is going to be just g times h. And then if I will calculate this v, it is 2.83 meters per second. If I will repeat this with using the I different, because here I did use I equals mr squared. If you repeat that using the one for the cylinder, you will get a velocity that is 3.3 meters per second, which means the cylinder is going to win the race here. This is the summary of chapter 10. Describing rotational motion requires analogies with position, velocity, and acceleration. Okay, the same we did with linear motion. This is the period, and this is just a summary of all the equations that we use in kinematics. And here we are relating tangential speed to omega, centripetal acceleration, and tangential acceleration. For rolling motion, we know that this equation is valid. And for kinetic, it is 1/2 I omega squared. The moment of inertia can be calculated as the summation of m times r squared. When the object is continuous, we did calculate this using calculus, and this is how we did obtain the equations that you're gonna use from the table. Kinetic energy of the object rolling without slipping is gonna be both rotational and translational. And when solving problems involving conservation of energy, both rotational and linear kinetic energy must be taken into account.